very, very, very small compared to the electrostatic or electric Coulomb factor 1 over 4 pi epsilon naught, 1 over 4 pi epsilon 0. Very, very small. And this is linked to the fact that gravitation is the weakest interaction we know of today. It's the weakest of the 4 fundamental interactions. It's about 137 times weaker if you compare, of course, masses and charges and so forth, than the strong nuclear interaction. But gravitation is incredibly weak. Okay. So this is the difference between G and K, right? Then G, another funny thing about gravitation, the gravitational interaction between this table and me is independent of the medium the system is contained in, sorry. So if this table and myself would be at the same distance, but underwater, in water, in air, in vacuum space, if there would be something in between, some other material medium between me and the table, the value of the gravitational attraction between the table and myself is not changing. If you speak about the gravitational attraction between the table and me. So G, the big Newtonian G, is independent of the medium. On the other hand, the Coulomb proportionality factor K depends on the medium. The epsilon naught is the value of the dielectric constant for vacuum, but if you are into air, epsilon is slightly bigger, right? It changes value, and so forth. So it's medium dependent. Then we believe, at least this is true in classical Newtonian physics, that gravitation is always attractive. Things fall down, they never go up. For the electric forces, it's not true. Electricity, the electric interaction can be attractive and repulsive, right? I have to say, though, that there are, in modern physics theories, things which cause gravitational repulsion. And these are strange things, like the energy of quantum vacuum and so forth. And in cosmology, modern astrophysics and cosmology, you might have heard about dark energy, which seems to dominate the content of our cosmos nowadays. And that thing seems to cause gravitational repulsion. Because the presence of dark energy in the universe seems to cause an accelerated expansion of the cosmos. Gravity should slow down. If you throw something in the air, what happens? Usually. But after a while it should fall down, hopefully, unless you give it an enormous speed. So gravity tends to slow down things. But the universe, the cosmos, is expanding, you know that. But the problem is that the expansion of the cosmos is accelerating. Well, it's like a strange turn into the gravitational field equations. Let's say that. And then there's another thing called a similarity between gravity and the electric force, is that both forces are conservative. That's a physics thing, isn't it? It means that the work, force times displacement into the direction of the displacement. Remember, F times F, projected F's, okay, times delta S. Okay, that work, mechanical work, is independent. Sorry, that mechanical work, in order to displace an object from one point to another point, is independent of the trajectory which is used in order to displace the object. That's true for gravitation, and it's very important. And that seems to be true, and is true for the electric force as well. So it's very interesting. But as I told you, the most important concept that has been developed quite slowly, of course, if you look at it historically speaking, is the concept of field. Remember the emphasis on the concept of field. The field is the main actor in electromagnetism, truly speaking. It is the new actor. Physics with electromagnetism, if you want, has welcomed a new actor on the stage. And that actor is called the field. In this case, it is the electric field. There will be you can speak about the magnetic field as well, and we will speak about the electromagnetic field, right? So how do you define a field? What is this field? Well, as I told you, in physics, if you want to define a new thing or a quantity, which is then physical, you should be able to define how you measure it. So, what is the possible procedure? Well, first of all, in this class, in this lecture theatre, the question could be, is there an electric field here above this table? In this point, is there an electric field? And how do I measure it eventually? Well, you take out of your pocket a test charge, a little particle which has a given arbitrary, possibly small, so you don't perturb the situation, a possibly small electric charge. This is a test charge, right? Test particle. Why is it called test charge? It's a small particle, I repeat, which has a given electric charge, expressed in Coulomb. The unit is called nowadays Coulomb. You take this electric charge, test charge, you put it in that point at a state of rest, and you leave it there, and you watch what happens. If this charge starts accelerating, if this little particle starts accelerating in some direction, it means, physically speaking, it undergoes the action of a force. You have to eliminate gravitation. Now we are speaking about electric force here, of course, yes? And the effects to which the electric charge is sensitive to. So, electric force. And so, if there is an electric force F acting on the test charge Q, you can deduce, in that point, there is an electric field. There is an electric field. And you can repeat the experiment in all points of the space, anyway. And how do you measure it? Well, suppose you know the value Q of the electric charge. Well, you just, from the acceleration, you could deduce the value of F. Or you could measure with a wire, a dynamo. You can hang, you can bound, you can bind, your charge, or attach your charge to a dynamo, and by measuring the length variation of the dynamo, you can deduce the value of the force F. So I can measure F, F is measurable. And if you calculate the ratio, the force that acts on the test charge, that's the value of the intensity of the electric field E. So E equals F over Q. And it is expressed in Newton per Coulomb. That's the unit measure, that's conventional. But the fundamental thing is the operational procedure in physics. It's the most important thing. Right, and the electric field is not an object which you are used to in Newtonian mechanics. Because in Newtonian physics, what are you used to? Tables, chairs, spheres, tiny particles, all material objects and all well localized. You understand? Well defined position in space or volume, finite volume of space. Here you are introducing a concept, which is a field, and that is a delocalized entity. It has no meaning to say that a field has a position in space, but it has meaning to say that the field has a value in any point of space, if it exists, if it is generated, if it is present in space. And another thing of the field concept is it's a bit ghost-like, because it's totally immaterial. So it's non-mechanical, in the sense that it is delocalized in space and it is expressed mathematically through functions of space coordinates x, y, and z, if you want, if you are in three-dimensional space. And it can also change in time, so it should depend mathematically if it is a function in the truly analytic sense of the word. It is depending on four variables, x, y, z, and t. And it is depending and defined at any possible points of space. So, it's the concept of field. And the same thing happens for a magnetic field. The procedures changes very slightly, but it's very easy as well to define. The fundamental concept here is the field line. Once you calculate the vector E, you can define the field lines to be curves in space, along which the vector E is always tangential. If you pick a point in the figure there, and you draw the tangent line, you get the direction of E in that point. And not only the direction in the sense of line, but also the true sense of the line, right? From left to right or right to left. That is given by the vector E as well, I would say. So, we see here a positive charge and a negative charge which attract each other. In terms of field lines, it's very interesting. The field lines interconnect. The field lines go out of a positive charge and vice versa converge on a negative charge. So two oppositely charged objects, they link each other because an infinite number of field lines connect these things. If you look at a huge big molecule, it's the result, if you want, of a complex network of field lines, electric field lines essentially, so forth. So the electric field line is an interesting tool to visualize the electric field in this case, and so forth. So I'll say more about this, but let me just go on, otherwise I speak too much as usual. Oh yes, this is another interesting concept. Once you have the electric field, for instance, if you place an electric charge Q, not a test charge, whatever arbitrary charge, even having a big value in space, for instance here, on this table, there's an electric charge. This electric charge is altering, changing the physical conditions existing in the surrounding space, in the sense that it generates an electric field. That means that if I take my test particle, I'll put it here, it will undergo the electric attraction or repulsion due to the generator charge. And this kind of field exists all over space, so it's delocalized. Okay, and it's not a material object, so it seems to be very non-mechanical, and it will get much worse because the field itself, which will have